Hello everyone, and welcome to this advanced lecture on volume of fluid model. This particular lecture is part of our advanced course on multi-phase flow modeling using Fluent. In this lecture, we will go through all the details that are related to volume of fluid model and multi-phase flow modeling using the volume of fluid model within the software Fluent. So let us have an overview of what we will study in this particular lecture. First, we will have a review of all the basics of volume of fluid model that we studied in the earlier lectures. Then we will see how to set up the VOF model within Fluent. After that, we will discuss in detail all the user inputs that are required for setting up the VOF model. Then we will end with a summary and references. So just to remind you of the basics of volume of fluid model, the volume of fluid model is an Eulerian framework model. That is, it uses Eulerian equations for both the phases, but it uses a specialized treatment to track the interface, which is distinct from the Eulerian model and the Lagrangian model. So it is a special class of a multi-phase flow model. Within the volume of fluid model, flow around individual dispersed particles is also resolved using the interface treatment. Then governing equations are solved for mixture phases and it is shared by all phases. So mixture properties are used to solve governing equations and all phases share a single set of governing equations. This particular model is highly recommended or suitable for stratified or separated flow where a distinct interface is present between different phases. Before we go into detail of modeling multiphase problem using the volume of fluid model in commercial software Fluent, we will just have a review of whatever we studied regarding the basics of volume of fluid model in our earlier lectures. In the volume of fluid model, how is the modeling approach? We will just have a quick look of the modeling approach used in the volume of fluid model. That is what exactly goes on from the fundamental modeling point of view. In the volume of fluid model, as you can see, there should be a distinct interface between the continuous phase and the dispersed phase. The volume of fluid model tracks the interface and models the volumetric forces. A single set of governing equation is solved for both the phases using combined mixture properties. That is, the mixture properties are volume weighted or volume fraction weighted, and a single set of governing equation is solved using mixture properties. Two different governing equations are not solved for different phases. Now let us see what flow governing equations are solved. Flow around individual dispersed particle is resolved. All the phases share a single set of governing equations, which is solved by using mixture properties. This particular type of model is specially suitable for stratified and separated flows where a distinct interface is present between the phases. That is, the two or more than two phases that we are going to model should be separated by a distinct interface. Now this is the continuum equation which is solved by using the mixture properties. The momentum equation is also solved by using mixture properties. It contains the body force as well as the other forces which are to be modeled. Now we will have a quick review of what the volume of fluid model does in order to capture the force balance. Now the VOF model does not track interface directly. Motion of all phases is modeled in order to capture the interface. That is, a separate equation or a separate governing equation is not solved for just tracking the interface. What it does is solves the motion of the phases involved and indirectly captures the interface. Now this is done by solving advection equation of phase volume fraction. That is basically a continuity type of equation for all the n phases. Such type of equation is solved for n-1 phases. So it basically gets the location or motion of different phases, and by that it uses schemes to capture the interface. Now, is it sufficient to only solve this equation and get the exact interface, or do we need to apply some special numerical techniques to come up with the right interface shape? These are some basic questions that if we think a bit deeper we will be able to understand. For the time being, we will keep this floating in our mind for you to think over them, and maybe at the end of this lecture we will go over this question and try to answer it ourselves. Let us first understand the concept behind VOF. When you are using VOF, it is used for two or more immiscible fluids. It solves a single set of momentum equation for the mixture phase. Single momentum equation is solved. It does not solve different momentum equation for different phases. It tracks the volume fraction of each of the fluid throughout the domain. These are the three basic principles behind volume of fluid model. Now we will see application of this model. What sort of problems are solved using VOF? First is a slug flow. As we have already discussed, it involves a gaseous bubble inside a fluid, a slug type of bubble. Also, stratified flow or free surface flows can be solved using VOF. Next is the droplet flow or bubble or particle flow, where there is distinct interface between the droplets or bubbles and the continuous phase. These can also be solved using volume of fluid model. Dam break type of problems can be solved, which is a totally different field of problem, and these can be tackled using volume of fluid. Annular flow, which we discussed earlier, where there is a central annular channel of gas surrounded by liquid around the boundary. These type of flow can also be solved using volume of fluid model. As well as jet breakup, that is a single jet breaking up into different streams or droplets, can be solved using volume of fluid model. These were some of the applications. Many more problems can be solved, but these are some of the principal applications or common applications. So let us begin the next section, in which we will study the steps involved in setting up the VOF model. We will study one by one all the steps that are required to set up a complete VOF problem. So let us see the steps involved in setting up the VOF model. This is the first step. In this, we import the mesh file. We check the mesh. That is, we click on this after importing the mesh file. After that, we scale the domain as needed with the dimensions that we want and the units that we want. After that, we select the solver. That is here, whether we want to use the pressure based solver, the density based solver. We also select whether the problem is transient and steady by clicking on either of the two. So this is the initial first step. Next step is to turn on the multi-phase model. For this, we go into problem setup, then to models, then multi-phase, and then select volume of fluid under the multi-phase model panel. This is how the initial main fluent panel looks like. Under problem setup, we enter into models. These are the models that can be used or that can be modified or selected for our problem. We select the multi-phase model. After that, this multi-phase model panel opens up. We select volume of fluid, which is here. Other options are mixture, oil area, and wet steam. So this is our volume of fluid model, and this is how we turn it on. The number of phases that we have to consider for our problem are entered here. So the process to turn on VOF model is to go into models, under problem setup, select multi-phase model. Within the multi-phase model panel, select volume of fluid and enter the number of phases. Next step is to define the phases that we have selected. That is, define their properties, define their material properties, define how they interact, etc. So for defining phases, we go into phases within the problem setup. All the phases that we have entered in the VOF panel, those many number of phases will appear here. To give material properties and various other properties to the phases, we click edit. After we click edit, the panel for those phase appears. First is the primary phase, then next is the secondary phase. As you can see, primary phase panel has opened up. Name is gas, and we can select material for that phase here. We can also edit the properties of the material by clicking edit. Once we have selected the phase and material and defined them, we click OK and proceed. Once we have defined different phases in our model, these phases will interact with each other. The interaction can be in the form of drag force, lift force, collisions or slip, heat exchange between different phases. Also, reactions may happen between different phases, as well as surface tension exists. We need to define all these interactions. When we define these interactions, the phases will behave as they behave naturally. Fluent allows you to define all these interactions. In order to define these interactions, we need to go into phases, select that particular phase, and then click on interaction button. Once we click on interaction button, the phase interaction panel pops up. We can define various interactions here. There is drag, lift, collision, slip, heat exchange, mass transfer, reactions between different phases, surface tension, etc. We can define any of the interactions that we want. It is not necessary to define all the interactions, but depending upon what physics or what problem we are modeling, we need to define those respective interactions. Once we define them, we click on OK and the phase interaction is defined. So we have defined phases, we have defined material for the phases as well as phase interaction. Once that is done, the next step is to define the phase behavior at the boundary or the domain. We need to define how the phases behave at the boundaries that we have, like velocity inlets or pressure inlets, outlets, walls. We need to define how the phases behave at these boundaries. Also within the domain, we need to define how these phases behave within the domain, that is within the cell volume. For this, we go to respective boundaries, like here as shown, we have selected wall boundary. First, we need to select the boundary entity. Then we select the phase, that is either the mixture phase or the phase 1 or phase 2. And then we can define different behavior of these phases at these boundary. That is, at wall we can define the contact angle for wall adhesion. We can also define thermal behavior, radiation, etc. Once we have defined the boundary conditions, the next step is to set up the different solver settings. Within the solution methods, within solution section, we have different schemes and different discretization schemes and accuracy schemes, like first order, second order, etc. Here, for individual models what we are going to use, we may get a scheme for a volume fraction like geo reconstruct or quick and any higher order schemes. So we set all the different solver rated parameters within this. Then we initialize our solution. We define any monitors or any other solution control that we want to define before we start the run, and the last step is to start our run. Now we see the last step in our setup of the VOF model. In this, we select the solution method and we proceed to calculate the solution. We select the solver schemes, that is, we go into solution, then solution methods, and select solver schemes or discretization schemes for each of the equations. We select the pressure velocity coupling, then we select the spatial discretization schemes for gradients, momentum, volume fraction, and energy. Volume fraction is an addition when we use the multi-phase VOF model. We have to select volume fraction schemes for the volume fraction calculation as well. This we set the URFs, that is the under relaxation factors. After this we set the monitors, that is the parameters that we want to monitor while the calculations are running. And lastly we click on calculate in order to start our solution. So this completes the setup of the VOF model. We would like to say thank you for watching this particular lecture. If you have any doubts, please contact us on our email address. So thank you for viewing this particular lecture within the advanced course of multiphase flow. See you in the next lecture.